So today we'll be discussing about how to create finite state machine using HDL Designer and how to simulate the same with QuestaSim. So, but before that, the most important part of it is what exactly is FSM and why we are today keeping our session with respect to FSM. So FSM is an integral part of VLSI. So because in any chip design, so what we have to do is we have to have sequential design. So for sequential design, you need to have finite state machines. So finite state machine is a part of any VLSI chip, so which is used for various applications. So what is a state machine? A state machine or a finite state automation or simply a state machine is a mathematical model of computation used to design both computer programs and sequential logic circuits. Which means what it states is there is a machine which has finite number of states, so which has a limited number of states, and so it is used for sequential logic design. That is, it is interrelated. That is nothing but we'll be having clock in our design. Say here I have two examples. One is a turnstile. A turnstile typically you would have seen in normal metros or bus stations, where after you are showing your ID card or pass or insert the currency, this turnstile will be turning at particular degree. So what we can say that uh, inserting coin is one state and then rotating is another state. So it is a simple FSM. Next we are having next I am showing one more simple FSM, that is nothing but your on and off of your bulb or your light. So what we'll do is first we are going to click on button or turn on the switch. That time your bulb will glow. So if you turn off the switch, the bulb will get turned off. It is nothing but it is again a finite state machine. So one more simple example that I can tell you in day-to-day life that we are familiar with is nothing but traffic light signal. So in traffic lights you can see the three colors, right? So one is red and another one is yellow and another one is green. So when we are in motion, the state will be green in color. So when we have to stop immediately, it will be yellow in color. After that, if we have to stop completely before proceeding, it will be red in color. So it will toggle between the three states. That is nothing but state 0, state 1 and state 2. So this is a real life example of where state machine has its use. So typically, as such, we are having so many other state machines also. So the two examples that I have depicted is a turnstile as well as simple on and off of a tube light. So next, what are the types of FSM that we are dealing with today? So here, basically, in finite state machine, we have two types of machines. One is Moore machine and another one is Mealy machine. What exactly is the difference between Moore machine and Mealy machine? So in Moore machine, it is a finite state machine whose output values are determined solely by its current state, which means the output here you can see in the diagram, it depends only on the current state. It does not depend on previous inputs, etc. But whereas in Mealy state machine or Mealy machine, it is a finite state machine whose output values are determined by its current state and the current inputs. So if you are basically looking at the both the diagrams that are depicted in the presentation, both are one and the same, except the fact that here we have an additional input that is going to the output combinational logic. But whereas in Moore machine, we are not having any such input that is going from input to output combinational logic. So basically, this is the difference between Moore and Mealy machine. So to elaborate on both these machines, what I have done in this presentation about FSM creation using HDL Designer is I have constructed Moore machine as well as Mealy machine, and I have simulated and I have checked the difference. What exactly do I get for a same pattern? What I have taken is a 101 pattern. So I am going to check whether the 101 pattern I am getting the two output and how the construction of Moore machine as well as Mealy machine is going to take place in HDL Designer. So what is the example I have taken for More FSM? So what is my aim is I have to find 101 overlap pattern using More machine. So what are the inputs that I am having? So there are two inputs. One is clock and reset. Those are the primary inputs that you get when you are launching HDL Designer as a default window. So then next one more input we are creating ourselves, that is capital X. So I have taken X as an input and Z as an output. So I will be giving my test vectors through X and I will be observing the output through Z. So here in the right hand side, you can see the typical construction of a More FSM. So how is this exactly More FSM constructed? So here there are four states: state 0, state 1, state 2, and state 3. So what we want is, our aim is to find 101 overlap pattern. So then next, this is the input that I am going to get, and I have to observe what is my output. So this output I will be showing in the waveform window in the Questa sim, and the number of states used are 4. So I will be telling you why this output Z is delayed by 1 clock cycle. So here we have 4 states: S0, S1, S2, S3. Let me go straight to S0. S0 is nothing but S0 is nothing but the default state where you have reset inserted to it. So reset is active low reset. So if we are giving reset is equal to 1, your state machine starts to work. So now S0 is there, right? So in that, what we are having is, we want to find a pattern of 101. So when the first input is 0, so the state 0 will be the current state, which means when the input is 1, the state will be current state itself. It will not go to next state. So when input is 1, it will go to next state, because we have the required 1 from the first 101 pattern. So when X is equal to 1, and it will go to state 0 to state 1. So this is the condition that I have given. And what is this Z is equal to 0 is nothing but output. Z is the output that we have declared. So Z is equal to 0 indicates that unless or until you find the complete pattern, you will not get the value Z is equal to 1. So after finding complete 101 pattern, you will get output Z is equal to 1, which will indicate that the state machine has detected the given pattern. So first we are having state 0. So after that, it has moved from state 0 to state 1 when X is equal to 1. So we have got 1 here. So it has moved from state 0 to state 1. So the next, what we want to find after 1 is 0. So after 1, we have to find 0. So which means, if X switches from 1 to 0, it switches the states as well. So what condition I have given is, from state 1 to state 2, it has to move. X should be 0. And Z is 0 because we have not yet completed the pattern. And what happens if X is equal to 1 again? So X is again 1, it will stay back in the same state. It will not go back to S0 because already 1 again it has detected. So that is why it is present here. So after that, after finding pattern 0, we are going to state 2. State 2 we will analyze. Next, if we are getting 1, your Z will be 0. But say for example, if you have got 0, if after 1 0 you find 0 again here, then what will happen? From state 2, it will directly move to state 0, because again we have to start from first to find the pattern, or that is the first one in the pattern. So again it will move to state 0. Say for example, after 1 0, that is 1 and 0, if you have found it here, and after that you got 1 here. So after 1 0 you got 1, so it will move from state 2 to state 3, and then it will make Z is equal to 1. So Z is equal to 1 will indicate that it has found the pattern 1, 0 and 1. Say for example, again we have found the pattern now. So what about after finding pattern, does it go back to the original state? No. Why? Because it is an overlap pattern. It will try to find, if after this one, if 0 is there, it will continue from the state which has already this one pattern, that is nothing but S1. So S1 detects X is equal to 1, so it will move state 3. If X is equal to 1, again it will move from state 3 to state 1. Say for example, it found a 0 after this. if you have a 0 after this, it will move from state 3 to state 2. And so we will be finding one more overlap pattern. So again, if after 0, it will you will get a 1 as an input. So this is about Moore machine. Here you can see that we have used 4 states and we have analyzed the logic. So here one more thing, if you are observing very keenly, in the transition arcs we have only the input, that is x is equal to 0, and in the states we have the value that is stored, output value that is stored, that is z is equal to 0, like that. We are not having any output values on the arc or transitions. So nor we have any input at the states. So this is about Moore FSM. So let us analyze how what will be the pattern for this output x, for this input x. So first 0. First we are giving input 0. So first after reset it will go to state 0. State 0 is the default state. It will look for 0, but we want one pattern, so it will remain in the same state. Next again one input will come. Input 1 will come. So after that it will go to state 1. So after state 1, we need if 0 will come, it will move from state 1 to state 2. But now we are getting another one, so it will remain in the same state. So after this one, again we are having one more one, so again it will be in the same state. So after this one, we are getting a 0. So after 1, we are getting a 0, so it will move from state 1 to state 2. So after 0, again we are getting a 1, so it will move according to the condition, it moves from state 2 to state 3. And after 1 we are again getting a 0, so it will go back to state 2. So this is the one we are getting, but we have the output z that has 0 0 0, all zeros are there except at the last stage where you will get 1, because the pattern 101 is only found at the last stage. Here 101, after that only you are going to get the output 1. So why we are getting, it should have been the output should have been instantaneous, but it will be delayed by 1 clock cycle. That is the most disadvantage of Moore state machine. So that can be overcome in Mealy FSM. So we'll look into it as to why it has got delayed and how Mealy can be better than Moore finite state machine. So in this example, again the overlap pattern is 101 again, and finite state machine has been constructed with respect to the 101 overlap pattern again, and we have the same two inputs, clock and reset. The same input I am giving here also, and I want to check what is my output. So here you can see that in Mealy FSM, so as I already told about the definition of Mealy FSM, it not only depends on the current state as well as the current inputs as well. That is why in the transitions or arcs you can see the both input and output. So in every transition you can see input and output, and we don't have any output value assigned to the states, either state 0 or either state 1 or state 2. We were not having previously in Moore FSM. We had z is equal to 0 that was attached to S0. Similarly for S4 we had z is equal to 1 assigned after finding the pattern, but here we are not having any output. And one more thing is that here also we are having the same reset. So let us start to analyze how to construct this Mealy FSM. So we are having this FSM now. So this we have a default state of S0, and for x is equal to 0, that is if you are finding, we want to find a pattern of 101. So we want to find a pattern of 101. So first, if x is equal to 1, if it is finding, only then it will move from state 0 to state 1. That is this condition. X is equal to 1, it has found, and output is not at 1 because it has not found the complete pattern. So this is one transition, and another transition is from to itself. That is x is equal to 0. Since first is not x is equal to 0, it will remain in same state until it finds the first value to be 1. So after moving to state 1, now immediately after 1, it has to find the value 0. So if it finds the value of 0, it will move from state 1 to state 2. Here you can see that x is equal to 0 and z is equal to 0. So after finding 0, it will move from state 1 to state 2 via this transition. So what happens after 1 if you are getting 1 again? So after 1, if you are getting 1 again, it will remain in the same state and it will wait until you get a 0. So after getting a 0, what we want is to have a value of 1. So after state 2, we are having a value of 1. So it will go back to from state 2 to state 1. So immediately it will display Z is equal to 1. But whereas in Mealy machine, the disadvantage was it had 4 states and it had to wait until the next clock edge for the value to be changed. But whereas in Mealy FSM, immediately after it finds x is equal to 1, it displays the output, immediately goes back to the state to find another overlap pattern. So in this way, the output of Z you will get without any delay. As compared to previous, we had a delay, that is this one was coming at this point. But whereas now we are getting exactly at 101 interface itself. And the number of states are also reduced here. So what we can, so the advantages of using Mealy over More is the fact that, so in More machine, now we can correlate that in More machine, if you are using, the power consumption will be more because you have more number of states. So in Mealy FSM, we have fewer states and fewer transitions. So that is why we will get lesser power utilization in the chip. So whenever we are coding any FSM in either HDL languages, say VHDL or Verilog, we can prefer Mealy FSM. But comparing to More and Mealy, both have the advantage and disadvantage, because if you are using More FSM, we have a clear-cut idea of how to define everything. But whereas here we have the, it depends on the current state as well as current input. So if input changes, automatically the state also will be changed. So that is the main disadvantage of Mealy FSM. So we have to carefully choose in our design whether to go for a More FSM or Mealy FSM. And we can, if for the same pattern I have written both Mealy and More FSM, it can be possible for any other pattern of our choice. So now coming back to our HDL Designer. So HDL Designer is a mentor graphics package that is available with higher education program too. So what exactly is a HDL Designer? HDL Designer tool provides highly automated environment for managing and exploring HDL designs. That is nothing but we can analyze, we can reuse, we can create, and we can manage all the files in HDL Designer itself, and we can graphically program finite state machine as well as truth table and symbols, block diagrams, etc. All those things can be graphically done in HDL Designer. And what are the other advantages? The design data is maintained as a source VHDL or Verilog files, which can be created or edited using HDL text or graphical editors. That is nothing but HDL Designer has graphical editors where you can edit your HDL code and organize and compile in the same environment. The main design manager window provides library management, data exploration, and design flow control facilities. So all those things are present in HDL Designer. Display the structure and hierarchy below any design object and compile VHDL or Verilog for individual views of hierarchy. That is, if you are graphically constructing a truth table or a block diagram or a IDB, or you have inbuilt Verilog files, all those things can be compiled under the hierarchy of HDL Project Navigator. And the structural HDL views can be rendered as a graphical block diagram or an IDB view. So we have graphical blocks also. So using graphical blocks, we can manage and we can compile all the different views in HDL Designer. So HDL Designer is one of the beautiful package in mentor graphics. So it is a very good software for learning, and especially if we are new to coding, we can develop our own state machines and we can automatically generate VHDL or Verilog code. And the advantage of HDL Designer is it can integrate with other simulation as well as synthesis software. So we need not worry about launching the software separately. We can directly launch from HDL Designer interface as well. So today I will be linking my Questa sim with HDL Designer software for simulation purpose. So basically what I have done is we have seen the overlap pattern of 101, right? So the same pattern, or I can say the same finite state machine I have constructed in HDL Designer. That is, it has state 0, all the 4 states for More FSM, and I have given all the transitions and arc corresponding conditions I have given, and I have simulated that. So after simulation, what I have observed is So these are the four states I am having: S0, S1, S2, S3, and I have a clock and I have a active low reset. Then I have input X and Z as my output. What is my current state and next state is being displayed in the waveform. So I give a pattern of 0, 1, 1, 1, 0, 1, 0 as per the discussion we had previously. So what do we get as an output? Z is 0, 0, 0, 0. Only at the last instance we are getting 1. Here you can see that 101 is pattern is already detected here. The output should have been, the Z should have been 1 here itself. But we are getting a delay of 1 clock period. So after 1 clock period, you are getting the output Z is equal to 1. So this is the thing I have observed in HDL Designer. With Mealy FSM, we are having a delay. So what about Mealy FSM? So Mealy FSM also I have constructed as per the specifications that I have given in the previous slides. So accordingly, I have given both input and output in the transitions, and I have simulated the same. So what is the simulated result that I am getting? So here I have three states because Mealy is much more optimized compared to Mealy, and I have a clock here, and I have reset, and I have X is equal to X value. I am having X as an input, and I am having Z internal. Z internal, since I could not use Z as an output directly on the transitions, I have used internal register Z underscore int to display my output. So I'll consider X as an input and Z as an output temporarily. I have assigned Z again, Z int as a Z again. So I'll be copying the content of Z, Z underscore int to Z. So temporarily we'll assume that Z is X is input and Z underscore int is output, since I cannot use Z output directly. So considering X as an input, I have given the same pattern 0, 1, 1, 1, 0, 1, 0. So my pattern should be 101, which is present here. 1, 0, 1 is present here. And if you are looking at Z underscore int, we are getting the value 1 here. So that is immediately at the 101 juncture, we are getting Z is equal to Z underscore int as 1. So which will clearly tell that Mealy FSM has, if the value of the input changes, automatically the output is going to change, and it is going to change the states as well. Here if you are seeing below, already the state has been changed. So that is the reason that we are not getting any delay of 1 clock period. Immediately we are getting the output. So after getting this output, I am assigning back to Z, which will take one more clock cycle extra. So here you can see that Z is equal to 1 at this juncture. So now, how do we do? What I have shown in the PPT is completely how to, what is the direct result that I have obtained. But how do you exactly construct this, and how do you get this simulation done? Because most of us are very new to HDL Designer, and we want to work and construct, and how to construct FSM using HDL Designer itself. For that, let us go back to the software. So I'll be using HDL Designer software. So here you can see the design, analyze and reuse, manage, and it is from Mentor Graphics. It is a Mentor Graphics software package. What I'll be doing is I'll be constructing the states or FSM here, and I'll be simulating for both Mealy as well as Mealy FSM. So if you're having a previous project, you can go for file, close project, and I'll go for a new project. Say I will give any name as, first let us start with Mealy FSM. So I'll give it as Mealy underscore FSM. Click on next. So this name already exists. So I'll just keep it as new. So I am going to click next. I want to create new design files. I want to graphically create FSM. So next I will go for a graphical view directly. If I want to add Verilog code, I can directly add here, but I am going for a graphical view. In that, I want to go for block diagram. First I want to select block diagram. From there I want to give inputs and outputs. So I'll select block diagram, click on next. So here again I have to give a new name. So Mealy I will give it as, so next. So this I will fill it up later. So I'll just click on finish. So here you can see that my block diagram window has opened, which is completely blank. I will add a block. So I have added a block and I'm going to add inputs. So this is my input. Now what I'll do, I'll connect my input to the block. So block is nothing but basically FSM. I'm going to assign it later. So I don't want to have a default name of signal 0. I want capital X as my input and I want Z as my output. So this is my block. What I'll do, I'll just double click on this. I'll go for graphical view and I'll select the state diagram. State diagram is nothing but a state machine. I will click on next. It is asking for block name. I will give again a Mealy FSM. So I'll click on next. So here you can see that the input and output, whatever we have given there, has appeared here. So I'll click on finish. So here, if you are observing carefully, so I'll just minimize this. So if we are observing carefully, what we can find is, we can find clock, that is positive edge of the clock. So whenever positive edge of the clock occurs or any event occurs, it is with respect to edge of the clock. And if what is this into mark, or what is the, how it is dealing with state 0. So it is nothing but if you are having any undefined state, it will, your FSM will reset and it will go back to state 0. And you have a active low reset and it will be reset to state 0 again. And we have a state 0 here, state here. So for my FSM, for Mealy FSM, I need to have 4 states: state 0, state 1, state 2, as well as state 3. I have my 4 states now. So what I want now is, I want to construct the transitions. So here I have an option of creating or adding any transitions. So transitions is used for declaring the inputs in case of Mealy FSM. So select the transition, and in our diagram, what is the first thing we have to do is, we have to have check for a transition in the same state. So what I'll do, here you can see that I want to loop it back. So I'm creating a loop back for the same state. So I can either, so I can just select this and a Verilog expression builder has popped up. So now I can give a condition that x is equal, if x equals 0, it should remain in the same state. So x is equal to 0, the value remains same here. And one more thing I want is z should be 0. So what I will do, I will go here, z is less than equal to 0, and I have to give a Verilog syntax file of semicolon. So I'll just select this, click on apply. So now automatically you can see that z less than equal to 0 as or 0 has been assigned to the output z. So now this condition is over. Now we have to go for one more condition, that is transition from state 0 to state 1. So I will use another transition arc. So now I have to give a condition that if x is equal to 1, x equals 1, move from state 0 to state 1. So I have got my transition here. So again, state 0, I have to assign it as z is equal to 0, because we have not yet completed the complete pattern. So now z is equal to or 0 is assigned to z again, because we have not found the complete pattern. So next I want transition within the same state, because to find if any more ones are there or not in the pattern. So I'll select this. So I'll give a condition of if x is equal to 1. So if x is equal to 1, remain in the same state. So with the help of expression builder, I am building up my finite state machine. So next, after s is equal to 1, I have, if x is equal to 0, it has to move from state 1 to state 2 as per the Mealy machine that has been discussed in the presentation. So what I'll do, I will select this transition, click here once and click on state 2, and here we can assign the condition. You can just close this and you can directly use this, and we want the condition for here to be x is equal to 0. So x equals 0. So this is a condition that I am giving. So now next, what again if we are detecting this 0, again if we are getting a pattern of 0, we have to go from state 2 to state 0. So for that, another transition. So I'll quickly complete this. So if we find again 0, go back to state 0. So then next, again after 1, we are finding 0. After 0, again if you are finding 0, go to state 0. If we are finding 1 again, go from state 2 to state 3. For that, a transition. So x equals 1 now this time. So this has been assigned. So here you can see that since there are two arrow marks, we have it as labeled 1 and labeled 2 here. And then next, what happens after finding x is equal to 1 here is we get an output. So here we have not yet assigned the output. We just select here and select as z is less than equal to 0 because we have not yet found the complete pattern. Click on apply, and here we can see that z is equal to 0 here, 0 here, 0 here, and only after state S3 at the S3 juncture we'll find z equals 1. Sorry, not 0, 1. Give a semicolon and then click on apply. So at state S3 we get an output 1, z is equal to 1. So what happens after finding 101 pattern here, that is 1 0 here and 1 here again. So what we have to do, how to find an overlap pattern? So we have to have the connection between S3 and S1 to find the pattern of 1 again. So for that we need a last transition. So so I don't have much space. So what I'll do, I'll just move this arc around. So this is more convenient now. So now I'll go directly the connection between these two. That is state S3 and S1. I'll just select this and I'll give x is equal to 1. X equals 1. So now click on save. So now we have this. So we have this complete condition. Our FSM is ready to find a pattern of 101. So I have just saved and I'll quickly run the design checker flow without checking. So here we are not having any errors and warnings here. So I'll just minimize this. So next we can, if you want, we can directly view the RTL code or Verilog code that has been generated by this finite state machine. So graphically we are constructing everything in HDL Designer and we are able to still generate finite state machine Verilog code. So this is the beauty about HDL Designer. So after this, what I'll be doing is I'll be launching the QuestaSim interface from here. So I have to, it is asking for a feature to enable. So I'll just click on yes, so that QuestaSim interface will be popped up. So now directly all the objects or input output ports will be added into the waveform window itself. So all the objects are here now. So let me select all the objects. So I'll just right click, add wave. So now these are the all four states of FSM, and X is input, Z is output. I'll just quickly rearrange for our convenience. So I want a clock reset X and Z, so which are ordered accordingly. So now since I have not written test bench, I will force the values. I want my clock to be given as a clock, and I'll give it as a default whatever frequency it has. And I want reset to be equal to 1 since it's an active low reset. I'm giving it as a 1. So I want a pattern of since I have an input of 0 1 1 1 0 1 0, I am going to give the first value of 0 and I will run once. So now you can see that 0, Z is 0 and current state is 0 and next state is 0. That is, we have just now started from state 0. So say state 0 is the default state. So let me go to X again force a value of 1. No, so now I will run for 3 times, or I will run for 100 nanoseconds 3 times, that is 300 nanoseconds. So I have a pattern of I have given input of 0, 1, 1, 1. So now you can see that it has gradually moved from state 0 to state 1. So now the current state is state 1. So what next? Now again I will go to X, modify the text vector that I am giving, give it as a 0, and again run for 100 nanoseconds. So again it has moved from state 1 to state 2. The next state is state 2. So now we have a 1 0. If again next 1 comes, if we are giving 1 at X and we are running for 100 nanoseconds, we'll get 101 pattern. So I'll go to X, click on force, give the value of 1 again, click OK, and run once again. So I have a pattern of 101. But did I get an output Z is equal to 1 immediately at this juncture? No. So what happens? Let me say I am giving one more value. Z is equal to 0 now this time. X is equal to 0. Input is equal to 0. So let me check whether I am getting an output. Yeah. So you can clearly see that Z is equal to 1. That is, the 101 has been, the pattern 101 has been found only after the delay of 1 clock cycle. So this is the thing about Moore finite state machine. So now let us go back to HDL Designer and analyze. So here it is asking for enable data capture and show animation. So if we are selecting this, we can clearly see the state transitions, that is current state and the next state. Click on yes. So here go back to FSM interface, come to the simulation time of the first clock period. So during the first clock period, let us observe where the state is in. So now it has completely, since it has completely run, it is in state 3. So that is the reason it is giving the final output as S3. S3 is the current state. So we have got an output of 1 only after the completion with 1 gate delay. So again going back to FSM interface. So this is the output that we have seen. So now we are confident of executing any pattern using Moore FSM. But we are observing a one clock period delay here. So that will be there in all the Moore FSMs. So now closing this interface, I will create a new project again, and what I will be doing is, instead of using a Moore FSM for 101 pattern, I will be using Mealy FSM. I will be constructing Mealy FSM, and I will be analyzing how do you exactly come forward and do the simulation for Mealy FSM, and how it is advantageous compared to Moore. So I will go for file, close project. I will go for a new project. So I will give it as Mealy FSM new project. So click on next again, and I want to create new design files. So graphical view, I want it to be a block diagram at the initial stage, because later on if I want to add some more blocks, I can add it later. So here entity name I am going to give Mealy. So next, click on next, and I don't want to add any port names here. I will add it later. So now this has popped up. So one more window has popped up, the same window. So now what I'm going to do, I want to draw a block, and I will assign this as an FSM. It is the same procedure that we have followed for Moore as well. So I want an input port. Again, I want a output port, and I am going to connect both of them. I don't want the default values to be signal 0 or signal 1. So I want it to be capital X and capital Z. So now I'll just click on save, and I want to assign this as a state diagram. Next, and give the block name. So this time we are going to do Mealy FSM. Click on next. So here we can see X and Z that have been assigned in the block diagram, that is being appeared here. So click on finish. So now again we are having the same window that has been appeared for Mealy. So before going that, I'll go to the signals table. So here what I will do is for Mealy FSM, I am going to change certain, instead of using comma, I am using registered, and here I have to give a default value of 1, and I will give reset default value of 0. So this is the small settings we have to change for Mealy FSM. So coming back to FSM, so we have we require 3 states here as compared to More FSM. So we want 3 states. So I have drawn here 3 states. So what we were knowing is for the transitions, we had we were giving only input to arcs or transitions here. For these transitions, we were giving only inputs. But how do we assign outputs as well? Can it be possible using HDL Designer? Yes, we can design Mealy FSM in HDL Designer as well, as like we have designed More FSM. So the same procedure I am going to follow. So let me go a little bit up. So here my condition is there. So for better visibility, I'll just drag it a little bit down. So here I have to give a condition. So I'll give first condition is x is equal to 0. So x equals 0, it should remain in the same state. Okay. So next I'll just adjust it so that since I have a few transitions to take care. So what I'll do, I don't want to assign any outputs to state 0. If that is the case, I would have just double clicked on this and given z is equal to 0 or something like that. But now I am not giving. I want to give it in the same transitions or arcs as well. So for that, what I'll do, how do you assign that? So for that, I will select this transition, double click, and here you can see x is equal to 0, right? Similarly, I want to give the loop back here. That is z is less than equals 0, because we have not yet found the complete pattern, and give the semicolon. So click on apply. Now you will get an error saying that replace all occurrence of z with z underscore int. So what it means is we cannot use output directly on the state machine. Instead, we can use a register and again assign the register value to the z variable or z output. Click on yes. Okay, so now default it has converted into z underscore int. So now click on apply. So here you can see a bar or a slash, you can say, that is differentiating between input as well as output. So similarly, I want to construct my complete FSM. So now I need to have a transition between state 0 and state 1, and I have to have a pattern of 101. For that, first input will be 1. So that is x equals 1. I need to find a pattern. So select this, again select the arc, double click on it, and give the value z underscore int should be less than equal to 0, because we have not yet found the complete pattern. Make sure you display or give the semicolon, else we are going to get error during simulation stage itself. And then here again we need to have a loop back to the current state, because what if we find the transition again? What if we find the condition 1 again? So for that, x, if it is equal to 1, remain in the same state. That is the condition I am giving. So I will select the transition. So z underscore int should be assigned as, it should be given a value of 0. So now we have input and output both, that is present in the arcs or transitions. So now we have found pattern 1, and now we have to go for 0. What happens if we get a 0 after 1? So select the transition here, assign it x. If x equal to 0, you go from state 1 to state 2. So click on apply. So it has applied. So now double click on this and give z underscore int should be assigned a value of 0, because we have not yet found the pattern. Click on OK. And now we have a 1-0 pattern, but we want last one pattern. So for that, we have to use one more transition from state 0 to state 1. So select this, give the condition that if x equals 1, again move from state 2 to state 1. So I have given this, and I have to give similarly the output. So now we can give the output. So z underscore int assign the value 1, because we have found the pattern 101, we can give the value 1. So what happens after finding 1-0? If we get another 0, that time we have to start all over to find the pattern. So for that, the final transition is, if we are getting 1 0, after that 1 again we are getting 0, go back to the default state. So x, if it is equal to 0, go back to state 0. That is the default state. So again we are assigning an output of z, because z cannot be 1, or z underscore int cannot be 1 for the pattern that has not been formed. So z, assign it a value 0 because it has not formed the pattern. So click on apply. So now you can see the both input and output here. So now this complete FSM is ready. That is, Mealy FSM has been ready for 101 pattern. Both the FSMs are equivalent. Only thing is, that is a More FSM previous example. Now this example is for the same pattern. It's Mealy FSM. So now I am clicking on save. So let me check. I'll just quickly go through the design to check if it gives any error. So no, it has not popped up any errors. So just minimize this and look for the code generated. So generally, if you are having an errors here, you are going to get all the warnings and errors necessary. So here you can see that it has created a new variable or a new register z underscore int. So now save and go to FSM interface from HDL Designer itself. So enable the switch to for FSM to get popped. So now we are going to give the same inputs and observe whether we are getting similar input or different from More FSM. So right click, add wave, and just remove the full path. So here we have, I'll quickly rearrange. So first I need to have clock. So next I want reset for better visibility. Afterwards I want input. Afterwards I want z int because I'm considering this as an output temporarily, and afterwards I'll assign z int to z. So now I have to force the values since I have not written this bench. For clock, I can instead of forcing, I will give it as a clock, force clock, and reset, since this is an active low reset, I'm going to give a value of 1 so that it will toggle the states. And x, as like previously, I'm going to give first 0 and run it for 100 nanoseconds. So I have run for 100 nanoseconds. So what next? I'm going to give a value of 1 and run it for 300 nanoseconds, or 3 times the clock pulse I am going to run. So 3 times I have run. So here you can see that it has transitioned from state 0 to state 1. Since still the output here has not come to 1 because we have not yet found the pattern. So for finding the pattern, we are having a 1. Now again we want a value of 0. We want a value of 0 now. Quickly run for again another 100 nanoseconds. So we have 1 0. Let me run one more time, give a value of 1 and check if I am getting output. So I have 101 pattern. Immediately it has displayed an output at here z underscore int. I am getting an output. So what happens if I am giving some other value one more time? Say for example, instead of 1 I am giving 0. Let me check if z gets the value. Yes, z gets the value from z underscore int. So z underscore int, after the next clock cycle, it assigns its values to output z. So if you are considering z int, so it displays completely immediately after finding the pattern. So this is the advantage with Mealy FSM. So going back to our HDL designer, so after enabling the animation, you can see that the default, the final state of after getting z is equal to 1, it has moved to S2. So what you can say that it is completely optimized. This Mealy machine has been completely optimized, and we are using fewer states and fewer transitions compared to More FSM. And FSM plays a crucial role in sequential circuits, and it is very important in day-to-day activities. Like for example, I have given a turnstile example. So where we are using day to day. So it is very important. And other applications like traffic signals or wiring or lighting, during the lighting times, if you want to turn on and off, or during the processor, if some event has to occur, it is waiting in a wait state. So all those things can be, it is very important on, it can be controlled by finite state machine only. So that is the reason finite state machine plays a very important role in the design of VLSI, especially. And understanding Mealy and More FSM, their advantages and disadvantages is crucial for any VLSI design engineer to progress with any particular application. So with this, I would like to conclude about finite state machine. And so you can get back to me at any time. So with respect to this, it is completely finished now. In here in the presentation, you can see that the same output we have got as like in the real time. So we had a 1 clock cycle delay, but whereas for Mealy FSM, we had the output coming immediately. Okay, thanks a lot, everyone. So with this, I have concluded the FSM creation using HDL Designer. So hope you can try and you can get back to me. Thank you.